Hello, dear students. Welcome to the last video of the present module, that is phase equilibria. In the last class, we discussed about system involving two immiscible liquids in contact and an important application of such system, that is steam distillation. Now in this video, we discuss a system containing two immiscible liquids and they contain a common solute dissolved in both. There is an important law in connection with this, that is called Nernst distribution or partition law. So the case is, for example, you have a beaker containing water which contain some benzoic acid dissolved in it. So water is solvent 1, and to which we add some amount of benzene, which is an organic solvent, that is solvent 2. What happens? Benzoic acid originally present in water layer will move to benzene layer and they get distributed between the two layers. We know that benzoic acid is more soluble in benzene, so it will be more present in solvent 2 than in 1. Anyway, the solute is soluble in both solvents and they get distributed between the two liquids depending upon temperature. So the Nernst distribution law states that the distribution of a particular molecular form of the solute between two immiscible solvents at equilibrium is a constant at constant temperature, irrespective of the amount of the solute and the presence of any other molecular species. So some points are very notable here. We have to consider a particular molecular form of the solute. That means sometimes solute may undergo association or dissociation, so that it exists in different forms in the two solvents. We have to consider only a particular form of the solute in both solvents to consider the distribution. The two solvents are immiscible and temperature has to be constant for this law to be valid. And this distribution doesn't depend upon the amount of solute. Means however amount you add, if you add 5 gram, if you add 10 gram, any amount of solute, that will get distributed between the two liquids in such a way that the ratio remain constant. So the concentration of the solute in the two solvent remain constant. That is the point. Remain constant if temperature is constant and it is independent of the presence of any other molecular species in this two solvents. So partition law can be expressed as C1 by C2 equal K, where C1 is the equilibrium concentration of the solute in layer 1 and C2 is the concentration of solute in layer 2. The value of C1 and C2 depends on the solubility of the solute in that particular solvent. That will be different. Solubility of benzoic acid in water is different from that of solubility in benzene. Then K is the expression for partition coefficient in favor of the first solvents. So that's also important. When we express distribution coefficient or partition coefficient, since it is a ratio, we should mention which solvent is taken in the numerator. So when we write C1 by C2, solvent 1 is taken priority. So we have to say that partition coefficient in favor of solvent 1, here water. If you write C2 by C1, then you should say partition coefficient in favor of solvent 2. Now, the value of partition coefficient depends on factors like nature of the solute, that means its solubility, the nature of the solvent, and also temperature. If we change temperature, partition coefficient may change. Now, for Nernst law to be valid, the conditions to be satisfied are: 1. Temperature should be constant, because when temperature changes, that may influence or affect the mutual miscibility of the solvent, and also it may affect the solubility of that particular the solute in each solvent. The number 2, solution should be dilute, because dilute solutions behave ideally. Number 3, 2 solvents must be immiscible. Of course, that is the first condition. We are considering 2 immiscible liquids or solvents. Number 4, the molecular state of the solute must be the same in both solvents. Sometimes the solute may undergo, as I said earlier, association in one solvent. So we have to consider the unassociated form of the solute in both, because that form exists in both solvents. Then number 5, no chemical reactions should take place between solute and solvent. Solute and solvent should not interact. Then this law gets violated. Now, thermodynamic derivation of Nernst law. See, like phase rule derivation, this is also based on the same key point coming from thermodynamics. What is it? At constant temperature and pressure, chemical potential of a component in 2 phases in equilibrium must be the same. That is a point based on which derivation is made. We consider 2 immiscible solvents 1 and 2 in contact, both containing the same solute in equilibrium concentration C1 and C2, and having chemical potential mu1 and mu2 respectively. Right? That is, as we have seen earlier, we have 2 solvents, liquid solvents in equilibrium. This contain the concentration is C1 and here it is C2 of the solute present in the 2 solvents, and they are in equilibrium. Now, chemical potential of the solute in solvent 1, we can write mu1 equal mu1 0 plus RT log A1, where mu1 0 is the standard chemical potential and A is the activity. Similarly, we can write mu2, chemical potential of the solute in solvent 2 is mu2 0 plus RT log A2. Now, at equilibrium, we already mentioned that the chemical potential of the same solute will be the same in the 2 phases which are in equilibrium. So, mu1 equal mu2. So, when we equate LHS, we can equate RHS also. So, what we write? Mu1 0 plus RT log A1 equal mu2 0 plus RT log A2. Rearranging, what do you get? RT log A1 minus RT log A2. Taking mu1 0 to the other side, you get mu2 0 minus mu1 0. Then taking common factor RT to the other side and writing the logarithmic term as log A1 by A2 equal mu2 0 minus mu1 0 by RT. At a given temperature and pressure, standard chemical potential is a constant. So again, mu2 0 minus mu1 0 is a constant. So we get log A1 by A2 is a constant because R is a constant and we have kept temperature constants. So RHS is a constant. So what we get is log A1 by A2 equal constant, or A1 by A2 is equal to constant. We know that for dilute solutions, activity can be replaced by concentration. So we get C1 by C2 equal a constant, that is partition coefficient. That's the derivation of Nernst law. Now applications. There are many applications for Nernst law. We discuss a few of them. Number 1, determination of solubility. See, suppose we are adding excess of solute to the system containing two solvents, solvent 1 and solvent 2. We are adding a solute which is soluble in both. We are adding excess. When we add excess, what happens? Depending upon the temperature, a definite amount will go into solution and the rest will remain undissolved. We call it saturated solution. So if an excess of solute is shaken with the two immiscible solvents in contact, at equilibrium, both layers will be saturated with the solute. Okay, then in that case, concentration C1 and C2 in the two solutions will be equal to the respective saturation solubilities or solubilities, that is S1 and S2 of the solute in the two solvents. By distribution law, we know C1 by C2 is a constant. In this case, when we are adding excess of solute, the C1 can be replaced by S1 and C2 by S2. So that represents the saturation solubility. So we can write S1 by S2 equal K. Right? That will be equal to the partition coefficient. So what's the application? If you see K is a constant for a given pair of solvents and the solute for a given temperature. If you know the solubility of the solute in one solvent, solubility in the other can be calculated using this equation. That's the application. Now, going to the second application, an interesting application, that is what is called distribution indicators. The end point of a titration involving a very dilute solution. If the solution is very dilute, titration will be difficult. That means volumetric analysis may be difficult in the sense it will be difficult to note the color change. In such case, we can easily detect the end point by adding a few drops of a suitable solvent which is immiscible with water, and then that solvent is known as distribution indicator. By taking example, we can understand this very easily. You know iodometry. Suppose you have a very dilute solution of iodine. This is not iodometry, iodometry. You have a direct titration of iodine with sodium thiosulfate. Using starch indicator we do it. If the iodine solution is very dilute, it will be difficult to note the end point using starch indicator. Remember, iodine is violet in color or deep brown or brownish violet. So for the titration between a very dilute solution of iodine against sodium thiosulfate, what you do? You add a few drops of an organic solvent, that is CS2, carbon disulfide, into it. So there comes a distribution system. There develops a distribution system. See, you have a very dilute solution of iodine here. What you do is you add a few drops of CS2. So it is a two immiscible liquid system now, water and CS2, which are immiscible. So iodine present in this water will move to this CS2 layer almost completely, because iodine is more readily soluble in CS2. Okay, so when entire iodine go into a few drops of CS2, that will appear as violet color. And now you add thiosulfate into it. You go for titration. Thiosulfate will react with iodine. You know the equation in iodometry or iodometry, redox reaction. So no need of starch indicator here. So if you add sodium thiosulfate into this iodine solution, it will react with iodine molecules in aqueous layer. Reaction will continue. So when iodine in aqueous layer get depleted due to reaction, now the iodine will come down from CS2 layer in the equilibrium, and it get reacted. So slowly that violet drop that is iodine in CS2 will slowly fade out, and you can easily note the end point looking at that CS2 drops. The point, one important point is that the distribution, the partition coefficient of iodine in CS2 against water is very high, about 400. That means iodine is much more soluble in CS2 than water. So a partition coefficient for iodine between CS2 and water is very high. That's why the whole iodine, almost all whole iodine get shifted to CS2 layer so that we can see the violet color. So this is called distribution indicator. And the third application is solvent extraction. What is solvent extraction? It is another important principle used in, a method used in organic synthesis. The process of extracting out a solute from one solvent, usually water, into another, there is an organic solvent, which is immiscible with the first. This is used in phytochemistry or extracting essential oils from various parts of plants. For example, if you extract eucalyptus oil or lemongrass oil from their plants, you will be getting a very dilute dispersion of these oils in water, and to a very small amount of these oils present in this aqueous layer is extracted by adding an organic solvent like ether or petroleum, benzene, etc., so that essential oils will get distributed quickly into this organic layer. So that is solvent extraction. Organic compounds in aqueous solution are usually extracted out into organic solvents like ether, benzene, etc. Generally that is done using an instrument called separating funnel. You might have seen this in the lab, like this. So what we do is, see, we have a system containing water, an aqueous solution of an organic compound. Okay, we have to extract this organic compound from this aqueous layer. What we do, you will add an organic solvent into it with which water is immiscible. For example, ether is added to this aqueous solution of an organic compound. Then you will pour this into this funnel and close it, and you shake it well. So it will be now like this here. The aqueous layer is down, suppose, and the organic layer is up. What happens? And you shake it well. What happens? The organic compound from aqueous layer will get distributed into organic layer more readily, because where it is more soluble, right? So the organic compounds is extracted out from the aqueous layer into an organic solvent. You will thoroughly shake this funnel and then keep aside for some time to settle. Then you open the tap, collect the aqueous part in one beaker, okay, and the ether layer or organic layer in another beaker. By evaporating of or distilling of this ether, you can get the organic compound. Of course, you know that the extraction may not be 100%. That means the entire compound from aqueous layer may not pass into the organic layer in one attempt. Means the aqueous layer may contain still more unextracted compound. So you have to repeat this procedure. Means you add a little more amount of ether, then put it in the funnel, separating funnel, and thoroughly shake, and again get extraction continues, and you can separate the two layers and collect it, and the process is repeated. So solvent extraction is done in a number of steps. So here comes a question, that is, what is the best way of extraction? Suppose you have an aqueous solution of an organic compound given, okay, an aqueous solution of organic compound, and you are given with a definite volume of an extraction solvent, that is an organic solvent. Here this is given. You have to extract the compound present in this aqueous solution effectively. So for more efficient extraction, that is given here, for extraction is more efficient when it is done in more number of steps with less amount of solvent. That means you add from the given solvent, organic solvent, you add a little amount of solvent at each time and mix it, put it in separating funnel, and then collect the organic layer, and it is repeated. So extraction is more efficient. You can extract maximum amount of the organic compound from this aqueous layer by doing extraction in more number of steps, taking less amount of solvent. That is the principle of extraction. It can be mathematically proved actually. Actually this is our common experience also. Suppose you are given a cup of water to clean a vessel, a utensil. What is the best way of cleaning? Cleaning is also a kind of extraction. The vessel or utensil might have some dirts or things attached to it. So we are washing it, we are extracting it out. So best washing is washing many times with little amount of water rather than just pouring the whole cup of water in a single step. So the same thing applies to solvent extraction, and it can be actually mathematically proven also. Now coming to the last application, that is study of association of a solute in a solvent. It's very important. We know that, for example, benzoic acid undergo dimerization in benzene. Like that, many solutes may undergo association. We can verify whether it is forming a dimer or trimer, etc., by studying this equilibrium. Consider a solute A, okay, existing in its normal form, that is monomeric form, in solvent 1. So this is the upper layer is solvent 1. And associated form you can see in the solvent 2 down, right? These molecules of A forms an associated form, maybe dimer or trimer, that is AN in solvent 2. Let the concentration of the two layers be C1 and C2 respectively. It's very important to note that C1 is the concentration of A, but C2 in the solvent 2 is the concentration of AN, not A. Okay, most of the A has changed into AN. So there's an equilibrium in solvent 2, that is N molecules of A polymerize into AN. So remember, C1 is the concentration of A in solvent 1, C2 is the concentration of AN, that is the polymeric form in solvent 2. Okay, now equilibrium existing in solvent 2. We consider the equilibrium in solvent 2, that is the polymerization, written here. Na gives An. So equilibrium constant Kc we can write An concentration by A raised to N. Clear? Rearranging it, what you get? A raised to N equal An concentration by Kc, or you get concentration of A equal N root of An concentration by Kc, that is equal to a constant into n root of an concentration, that's equal to a constant into n root of C2. So you have to be careful here. C2 is a concentration of which one? An only, not the amount of A present in solvent 2. But for writing partition coefficient or distribution coefficient, we need the concentration of the same molecular form of the solute in the two solvents. So that's why we have considered this equilibrium. So from this equilibrium we got what? We got the concentration of A, that is a monomeric form in solvent 2 from this equilibrium constant expression. So concentration of A is equal to constant n root of C2, where C2 is the concentration of the AN form of the solute in solvent 2. Now applying distribution law, concentration of similar species in the two solvents will be in a constant ratio, we know. So the C1 by concentration of A, that is the concentration of A in C2, we can write like C1 by concentration of A in solvent 2, okay, is a constant. Substituting for A, C1 by n root of C2 is equal to K, right? So we have written n root of C2 here because we have to consider the concentration of the form A only in solvent 2. Otherwise we write C1 by C2, but C2 here is the concentration of the polymeric form, that is AN, right? Now how we study the association, that means whether the solute undergo dimerization or trimerization, how we verify? We go to the crux of this experiment. What we do is we carry out several experiments, right, taking different amounts of the solute in the two solvents. So we get a list of C1 and C2 from various experiments. C1 is the concentration of A in solvent 1. C2 is the concentration of AN in solvent 2. Now what you do is you put in this formula, you substitute the values of C1 and C2 from different experiments in this equation, that is C1 by n root of C2. We know that it has to be a constant by distribution law. So what we do is, from the set of values of C1 and C2 obtained from experiments, first you put value for n equal to, okay, n is given 2, and then you find C1 by 2 root of C2, okay. Then you put value n equal 3 in this equation and substitute various set of C1 and C2 values, and you continue this. So the point is, you substitute the values of C1 and C2 in this equation, giving value of n equal 2 and then 3, 4, etc. Now for which value of n you get this ratio a constant, gives you the kind of polymer, the kind of association taking place, because partition coefficient has to be constant, you know. So for which value of n you get this constant, give you the kind of association. For example, in the case of benzoic acid distributed between water and benzene, if you study that system, you can see that in benzene, benzoic acid undergo dimerization, that means value of n equal 2. So in that system, if you take C1 by root of C2, isn't it? Root of C2 gives constant. That means by putting value for n equal 2, you get the constant K. That means benzoic acid undergo dimerization in benzene, right? So these are various applications of Nernst distribution law. So that's the end of the module. Thank you.